Okay, so good morning to all of you once again, and um, so I've given out the assignment to you folks. So did you receive that? Like in Teams, you could see that, or I also sent you a separate email. Any one of you guys? Did you? Yeah, Nayan.
Yes, yes, sir. We have
Okay,
received the mail and we
okay, cool.
can see it in the Teams.
Okay, and the question is clear, right? I hope there's no ambiguity in the question. It's essentially, the constitutive equations that we discussed and the coefficient associated with those equations. You need to find a relation. So if you look at the table that, yeah, so what I'm asking you is, the relation between these two and these two. So this is what I've asked you as an assignment. Right. Okay, so now I think we should do a little bit of circuits, and this is where this is what is closest to my heart actually. But so far I had to build a subject so that we can get into the circuits. So yesterday we talked about the figure of merit and how we can characterize or based on one parameter or based on some sort of an equation, how do we say that okay, this material has a better piezoelectric behavior than the others? So that we discussed, right? And so we also, I mean, more importantly, I think I introduced to you the concept of figure of merit because this you will come across in the industry for any design or any system that you develop or you make, right? People like to refer the design as a figure of merit because that gives you a quick understanding where the design stands. So basically each design, as I said, might have multiple vectors, right? One can be power, another can be performance, right? Another can be speed, right? So in performance, again, there can be many things like, for example, if you're talking of an ADC, it can be SNR or actually ENOB, maybe, right? Effective number of bits, right? For a sensor, for example, or the piezoelectric material, we K square we define as a figure of merit, and this makes sense because if it's a piezoelectric material, whatever input energy that we are giving, either be it in mechanical domain or be it in electrical domain, how well it converts that energy from one domain to the other, that is uh, that kind of tells us how good the material is, right? So so I hope there's no questions on this, and then we derive the figure of merit from first principles. So one thing, guys, you will see that I've tried to do throughout all my lecture slides, the equations that I'm showing. I've tried to build it from first principles so that nothing remains esoteric. I mean, there is nothing secret or nothing ununderstood from the equations that I have put in the slides. Even subsequently, you will see we will be dealing with larger equations, but I've tried to derive it from first principles so that you people can get a good physical understanding of the equation. There's no point in mugging up the equation, right? Because that's not going to fetch us anything other than probably grades. And grades, like everything else in life, has limited value. It doesn't. I mean, having a good grade is fine, but it won't serve you if you don't understand the subject, right? So what we said is K square is essentially a parameter which tells us how much of the energy, input energy, is converted from one domain to other. And we took this example, right? And based on this example, we derived K square for this kind of a setup. The input energy is electrical energy in this case, which is half CV square, and C also we know is epsilon A by D. D is the distance between the two plates, right? In this case, D is nothing but L, which is understood, right? So these are the two opposite plates, right? So this is L, and epsilon T. Why it is epsilon T? That also we discussed. because there is no stress in this given configuration. The material is free to move, and whatever deformation happens because of the piezoelectric behavior, the plates move freely, and even though there is strain, there is no stress, which means T is equal to 0, right? In this case, T is equal to 0. So when we are talking of permittivity, we are going to talk of permittivity at a given stress condition, which is T equal to 0. And then V is nothing but E times L. This is again pretty straightforward, class 11, 12 physics, right? And this turns out to be, whatever, half epsilon T AL E square, right? And the mechanical energy we know from, again, basic physics is half kx square, where x is the deformation. In this case, instead of x, the deformation is delta L. So, it is half delta L square. And k we have already derived earlier. In one of the earlier slides, you will see I have derived k, a relation of k and Young's modulus, which is nothing but inverse of the compliance. So we had derived earlier k is equal to ay by L, right? If you remember, a few classes back we had derived that. And y is inversely proportional to the compliance coefficient. And again, in this case, what compliance coefficient are we going to talk about? It is a compliance coefficient S with a constant electric field E, right? Because we have a battery connected here. So any additional charge that develops because of whatever stress that somebody else might put in on this force, I mean on the walls, right? Those charges will be swept away by the battery, right? So it is SE and delta L. I'm just rewriting this equation delta L as, I just multiply this by L square and the denominator also by L square, and I can kind of do this mathematical jugglery to put it in this form. And then delta L by L is nothing but strain, as we know, right? So this we can write as half AL by compliance matrix multiplied by the strain square. And strain, because it's a piezoelectric material, we know S will be given by D times E, where D is again is a piezoelectric coefficient, right? So now with this guy and this guy, if we go back and put the values here, we know, so we can see that k square is proportional to d square divided by epsilon t. And see, another very important thing, again, we'll even in the next few slides we will see, right? Any equation that we derive, we must try to intuitively check whether what we are saying makes sense or not, right? For example, the fact that the k square, a figure of merit, this will be better, can be easily understood by the fact that if the piezoelectric coefficient d that is higher, k square will be higher. That is intuitive enough, right? Similarly, compliance, right? So if the compliance is lesser, right? If the compliance is lesser, what happens? If the compliance is lesser, the k becomes higher. So does this have an intuitive feel here to this? Or even epsilon t, right? Epsilon t we can understand because essentially the input energy, higher will be the epsilon t, the input energy that we will have to give will be higher, right? So epsilon t, if that is higher, k square will again be lower, right? So for k square to be higher, the compliance SE needs to be lower, right? And this part may not be as intuitive, but this you can see based on whatever steps we have done. There is probably nothing wrong in that, right? Okay, so now what we will do is we'll try and look at a simplified model of the material, right? So because we are talking of something which, a material which we are, let's say, compressing, right? We are applying a force or whatever. So we can say that this material, when we release the force, what happens? We have compressed a material. When we release the force, what happens? It goes back to the original shape, right? Unless, of course, you have not compressed it to a point that the material characteristics itself has changed, or it has deformed to a point where it cannot go back, right? Unless you have not done something like that within reasonable mechanical limits. The material deformation that happens because of the application of a force, this, once we release the force, it goes back, right? So this behavior, or this kind of how to say characteristics, we can easily model by this kind of a system, right? This kind of a system you would have seen in many many of your other courses, right? Because this is a normal a spring and a mass example, right? So what happens is, we are comparing the spring and the mass and the damper. So this is a damper, this is a spring, not a resistor. It's actually a spring with a spring constant K, and this is a mass M, right? So we can model the complete behavior of the spring and the damper system, right? We can model the piezoelectric material behavior of the spring and the damper system. The characteristics can be modeled by looking at the mechanical characteristics, can be modeled by drawing an analogy with this kind of a system, right? Let's say we apply a force, and when we apply a force, this mass M, it moves a certain direction x. So this is the equilibrium position, x equal to 0, right? And the mass M is moving, and it has moved, let's say, a distance given by x, right? So then, how do we kind of write? How do we equate this? So the force F, and this is plain and simple physics, right? We are equating, the force that we are applying in x direction versus the force that is there in the opposite direction. Both the forces must be equal, right? So F will be equal to what? M times x2 dot. X2 dot we know, right? D2x, x2 dot is nothing but this, I think everyone will know. D2x dt square, right? So F will be equal to M x2 dot, right? What else? Plus the damper C times x dot plus K times x, right? This is a pretty simple kind of an equilibrium. If we equate the forces on both the directions, we can write this. So nothing, again, this is from first principles. We are not saying anything that cannot be understood by a class like this, right? So the same equation, if I take a Laplace on both sides, and if I do a simplification, so that means F as a function of S, the Laplace coefficient S will be equal to M x s square, right? Sorry, 1 second. Sorry. Yeah. So what we will write is F as a function of S is M s square xs plus C s xs plus K, right? xs. The same equation that I wrote, F is equal to mx2 dot plus cx dot, sorry, yeah, so cx dot plus k. I've just taken a Laplace equation, and if I take the Laplace, if I simplify the Laplace equation, I can write xs by fs, right? The same thing I can rearrange and write, and this is what we get. Again, not a big deal, right? We have derived this from first principles. It's very important to understand all this, because typically, when you look at textbook or maybe any other material, they will just say, okay, this is the transfer function, right? But where the transfer function is coming from, probably they will not even discuss. So, but it's important for us to understand from where the transfer function is coming from, right? So the same equation, again, I have just rearranged in the form. So this is a typical second order equation. So this, if I rearrange write like this, right? Is 1 by K S M by K, right? S squared plus C by K S plus 1, right? So the same equation I've just rearranged, and M by K, let's say, is nothing but omega n. Omega n is inverse of that, K by M, right? And eta by omega n. Omega n, what is omega n? Omega n is what? So this kind of an equation has a second order behavior, right? So it has inherently, it has an oscillation kind of a behavior associated with it, right? So the natural frequency of that oscillation, meaning if there was no kind of, let's say, damping, right? If the Cx dot was not there, if we release this, and if there is nothing to kind of, there's no friction or no energy where it is getting dissipated, then this guy will behave as an oscillator, right? So that natural frequency of oscillation is given by omega n. And what is eta? Eta behaves as a damper, right? What it means is, if we have an oscillation, we treat this as a sine wave, right? Now because we have this damper, what happens is this oscillation will slowly die down with time, right? The amplitude of the oscillation will slowly die down with time, and your final behavior, let's say your step response, will be something like this, right? This I think you must be aware from your control theory courses, right? So not a big deal. So all what I have done is, Xs is nothing but the deformation of the piezoelectric material, and F is the force that we had applied. So by simplistically, we took a second order model and we are writing the transfer function of the deformation as a function of the force that we have applied. That has a second order behavior. No problem, right? We have not done anything, again, significantly different, right? Okay. So this is my first equation. We are just to keep in mind what we are trying to do. We are trying to create a simplified model, an electrical model. When I say a model, it's an electrical model of the piezoelectric crystal. Because only then, if we have a model, only then we can put it in our electronic circuits, and then we can study the overall electrical behavior, right? So this is the first step. So second, we also know, so these are the basic fundamental relations that we have discussed. The polarization is proportional to T is what? T is the stress. So whatever, charge that develops, polarization is proportional to the stress, right? That we have discussed. And Q, so why am I writing P equal to dt as Q equal to dF? From where does that come? Polarization is what? Polarization is the charge surface density, right? So polarization P is nothing but Q by A. A is the area of the plates, right? So basically, if I write this equation again like this, right? P is equal to dt, right? And P is what? Q divided by A multiplied by dt, right? Is equal to dt. So T is what? Is the stress, which is nothing but force divided by area, right? So P is equal to dt. So if I cancel out area, because obviously area is not zero and it's safe to cancel, I can do this mathematical step. So P equal to dt can be written as Q equal to dF, right? Not a big deal, right? So similarly, S is equal to dE can be written as X equal to dV. Is this understood? Why this is happening? Right? What is X? X is the deformation, right? S is what? S is the strain. So the deformation, so S, if I write like this, right? X divided by L, right? This is the strain, right? X is the deformation. Please remember, X is deformation. So is equal to D times E, right? And what is E? E is nothing but V by L, right? So again, length is non-zero and it's safe to cancel out. So S equal to DE can be written as X equal to DV. Not a big deal, right? So in the electrical domain, the piezoelectric transducer can be modeled as, let's say, very simplistically, we have not brought in the mechanical behavior yet here. What we are saying is the piezoelectric material or the transducer, what does it give when we apply a force? It gives charge, right? So, but then force that we apply in real world, nothing is static, right? The force that we apply is a function of time. So similarly, the charge will also be a function of time, right? So instead of writing this as charge, what I can do is I can represent the crystal as a current source, right? And I have a capacitor in parallel to this. Why? Because the current, when it flows into the capacitor, if we integrate it, it will give us the charge, right? So very simplistically, I am writing or I'm modeling the behavior of the piezoelectric crystal. When I apply a force, I get a charge, but force is a function of time. So similarly, charge is a function of time. So instead of writing this as charge, charge has as such no physical, we cannot represent charge in electrical circuits, right? We have capacitor, resistor, inductor, current sources, voltage control voltage source, those kind of things. We don't write charge anywhere, right? So how do we represent charge? We represent charge by having a current source in parallel with a capacitor, right? Not a big deal, right? Any questions on this? Okay. So again, IN we know very simple, in very simple terms, dq dt. And what is q? We have got q here, right? We have derived q. So q, so f is what? So this is equal to what? F is equal to kx, the spring equation, right? F is equal to kx, right? So q is nothing but df is equal to, so basically if I write like this, q is nothing but dkx, right? K is nothing but the spring constant, which was given by what? Spring constant was given by, if you remember the last this thing, right? AL by the compliance matrix, right? AL by S, right? So dq dt is nothing but dk del x del t. So this we can write, not a big deal, right? So similarly, so now once we have gotten to this equation, it's just a matter of taking Laplace on both sides, transform on both sides, and if we do the transform on both sides, this is nothing but a differential, which we know from all the Laplace basics that a differential can be represented as S, right? Which we anyway this we are not going to of course derive. So In S by XS is equals dks. So this is our second equation. So the first equation, we had a mechanical equation where we related x, the deformation, with the force. The second equation, we are relating the current that is generated as a function of the deformation, right? So I'm building into the final model. So bear with me till we go to the final model. So In by xs is dks, right? So now we will have a measurement setup, right? I mean, whatever we are going to, I'm going to continue with the model, but whenever we are going to model, one, way to verify whether the model is correct or not is we have to, the mathematical model that we have derived, that we compare with measurements that can be taken, right? So we need to have a measurement setup also in the physical world. You can't say that, look, I have a mathematical model for this, and this is how it will be. You have to also give proof. You have to give results that okay, how your model matches with the actual material behavior, right? So you'll need a measurement setup, right? So what is there in a measurement setup? What will you do? So you will probably have some sort of wire. You will have a going to an oscilloscope or a voltmeter or whatever, and that wire itself, I've modeled the wire. You can put all sorts of impedances and all that, but here to keep things simple, I've just modeled the wire as a plain wire. However, I have shown another capacitance C subscript C here. This you can treat as a parasitic capacitance or the input capacitance of the so if this is my, let's say my voltmeter, where I'm going to measure the voltage across these two terminals. Now the voltmeter again will have some loading on the whole system. So this is my piezoelectric crystal, right? So this capacitance C will come as a stray capacitance. It can come either from the voltmeter that you are putting, or it can come from the wire that you have connected. It can come from anywhere, right? And this RL is nothing but the load. I mean, so if it's an ideal voltmeter, what should be the value of RL? If it's an ideal voltmeter, what should be the value of RL? In your measurements lab, any of your previous theory classes, that should be clear, right? What should be the value of RL, guys, for an ideal voltmeter? If this is a voltmeter,
Infinite.
yeah, correct. It should be infinite, because the job of the voltmeter is to measure the voltage, or in this case, the charge across this capacitor. But if I am so basically, it's like this, right? You go to a marriage function and somebody tells you to taste the food, right? And say that you are supposed to only say whether the food is good, or you are working as a just a food taster, or let's say the wine taster, right? Now as a food taster or a wine taster, you're not supposed to drink the whole wine, right? Because that's not your job. The job is to just tell whether the wine is of good quality or not, right? So similarly, in the process of measuring the charge across the capacitor, the voltmeter cannot eat the charge that was there and then say, okay, this was the charge, right? That is not how it should be. So in order to ensure that there is no charge that flows into the voltmeter, the characteristics that it must have is RL should be infinite, right? So pretty straightforward. So this is the transducer, this is the cable, this is the load, right? And so now we are trying to derive a transfer function of the piezoelectric crystal. So essentially, what are we trying to do? We are trying to study the voltage VL that will be read out by the voltmeter as a function of what? We are talking of a transducer. In this case, we are talking of this as a sensor, right? So we are reading the voltage that we are going to measure from the transducer or the sensor as a function of what? What should be the independent variable? Force, right? We should be our final goal should be to come up with a transfer function of this voltage that will be appearing across the voltmeter as a function of the force, right? So we will go there, but before we go there, this VL, if I represent the whole circuit like this, if you work out what will be the voltage as a function of these components, this will be this, right? RL, it's a plain straightforward voltage divider kind of circuit, right? So this is clear, right? RL divided by 1 plus. So these two guys come in parallel. IN anyway is my input source. So the amount of charge that flows into RL will be related to the relative impedance offered by RL and the impedance seen, the equivalent impedance seen by this guy. So this should be straightforward again, right? You can write the loop equations and solve it if you want, but this is how it will be, not a big deal, right? So then, but our goal was what? Goal was to find this. Our goal was to find the output voltage VL as a function of the force. So this expression can be rewritten. I'm doing just again some little bit of mathematical jugglery so that I can arrive to this point, right? I'm rewriting this as XS by Fs. What is XS? XS is the deformation of the crystal. By Fs, again, is the force, multiplied by In, which is the equivalent model that we have derived, by XS multiplied by VL by In. So if you see the same thing I have written like this, so In and In gets cancelled, XS and XS gets cancelled. So VL by Fs can be written as whatever this I have written, right? So now what we are going to do is individually we have found out XS by Fs in the first in today's first slide discussion. We looked at what is the transfer function of XS and FS. Then we also looked at IN and XS, right? And then we also, in the previous file, we derived this. Now, if we put all those three equations, equation 1, 2, and 3, and we kind of clean it up properly. So this, I think, we cleaned it up already, just that there was a K here. And, so this was, so if you clean it up, the equation, you will see it looks like this, right? Where tau n, which is the time constant of the circuit, and that is again should be obvious, even without doing the maths, you should be able to tell what is tau n, right? Because we have a resistor here in parallel with these two capacitors. So the time constant associated with it should be, these two capacitors are in parallel, and so is the resistor. So it will be RL multiplied by this equivalent resistance Cn plus Cc, right? So this is what the final transfer function will look like. Any questions on this? The way I have derived, meaning my goal is, as I said, not to give you the equation and say that look, this is the equation and this is how it is going to behave, right? The goal is to kind of develop an intuitive feeling of deriving the equations, and then because as engineers, when you join the hardware industry, you will see that you'll have to build solutions. You have to understand the underlying fundamental equations. Otherwise, you will not be able to do the design, right? So, what does this equation tell us? Any observations from this equation? Please look at. So from this, can we make a comment on what will be the behavior? What will be the voltage? So let's say we are giving a very low frequency force, meaning, so let's say we are applying a force with a very low frequency, let's say 1 Hertz. What will be the voltage that you will see in the voltmeter for a very low frequency force? What does this transfer function tell you?
It's linearly proportional to force.
No. See, this is the transfer function that relates VL with FS. My question is, I repeat my question, if the force that I'm applying, so this is force as a function of time, right? If I'm applying a force, which is a very low frequency force, right? Very low frequency. So why do I write the transfer function? What is the significance of the transfer function? Because the significance of the transfer function is, if I replace S with j omega, and if I plot the transfer function in terms of magnitude and phase, it will tell us the magnitude of VL by Fs. It will tell us for what amount of force, what will be the magnitude that I will get as a voltage output. So my question is, if the force that I'm applying is a low frequency signal to the piezoelectric transducer, what sort of, what will be the magnitude of the voltage that I will see in the voltmeter? Meaning I'm talking in terms of frequency domain. I'm not, I'm not saying, I'm not talking of DC characteristics, right? So for DC characteristics, so or let's say, so how to say this? So basically, again, going to the same point, if I have a force and I'm applying here, what will be the output voltage that you will kind of see? So if you see here, I'm talking of low frequency, and we have tau s coming in the numerator. So at low frequency, omega tends to 0, right? So if you see the problem with this kind of a measurement setup, if I am trying to measure the charge using the setup that I showed here, if I'm trying to measure the charge of the piezoelectric material in this kind of a setup, I land up in a problem. What is the problem? The problem is, at low frequency, if I have a low frequency force applied, because of S being on the numerator, the voltage output that I will get will tend to be 0. This is Any questions on this, guys? See, we derived the transfer function, and then by looking at the transfer function, I'm just replacing S is equal to j omega, right? We can discuss that also if you want, but that is not a scope of this course. Why we can replace S equal to j omega? But if we do that, right, S equal to j omega. So basically, this is nothing but a complex number, right? I mean, this is a complex function. Just that I'm representing the function with S to make my life easy. I'm representing the complex function algebraically, because we are in algebra is easier to deal with than complex numbers, right? But then I mean, we can do all the algebraic equations and then we can just replace S equal to j omega to see what will be the magnitude of this and the phase of this. Both are important. But my question is, what will be the magnitude? Meaning VL is proportional to Fs. That is no problem. I mean, VL, the voltage that you will see, is proportional to F. No problem. But what is the proportionality constant? If the proportionality constant itself tends to 0, then it's not a very good thing to happen, right? So basically the problem with this equation is, for low frequency measurements, using the setup that we had, using the earlier setup that we had, we will land in trouble because of the S appearing in the numerator. And on top of it, we also have this as a fraction. So for sure, dn divided by cn plus cc, this will also work as an attenuation, meaning it is going to, whatever signal you are going to get, you are going to attenuate it further. You are going to, if the signal is, let's say, originally, basically what is happening is, in this setup, the piezoelectric crystal is giving us some information. Let's say I don't have any of this and I'm applying a force, right? So the piezoelectric crystal is giving us some information in the form of charge, which I am representing as IN. But the problem is, when I'm measuring the information using this kind of a setup, the problem is I am consuming some portion of the charge myself in trying to. So again, going back to that wine taster example, right? I mean, your job is to just taste the wine, take as little as possible. Your job is not to drink the full glass, right? Because then you are going to lose the job. I mean, the wine has to be sold to customers to make money, right? So similarly here, when we are measuring the charge, right, we should not consume the charge of the information ourselves. But in this setup, if we look at the transfer function, which we derived in the next slide, in this slide, we are seeing that this is a problem that we have, right? I mean, we discussed so much of piezoelectricity, and we are trying to make this D coefficient as high as possible. We talked of K square. We talked of K square as a figure of merit, right? To make the material better and better. So we did all of that, and then while measuring it, we messed up, right? We came up with a system so that a low frequency force, when we are applying a low frequency force, we can't even have a proper voltage output, right? So this portion is clear, right? Any questions, guys? Okay. So this is actually a big problem. Gain at low frequency is a problem. So now we will see how to deal with it, right? If there is a problem, we have to find a solution. This is clear, right, guys? This is important for you to understand why this is a problem. And it's not just the maths. It is important, and I keep repeating it in the industry. Maths is going to be your tool, but it is not going to save you if you do not know how to use it. There has to be an intuitive feeling towards the maths. So it's very important to understand how this equation came, right? And then looking at the final equation, we are making some certain observations that look, in this measurement setup, we will have a problem of measuring the force. If the force has a signal, it has a low frequency signal, right? No questions, right? Okay. So now that we have the problem, let's try to solve it. Let's try to come up with a better measurement setup. So again, we have the same crystal, piezoelectric crystal, and we have the wire. And now we have an amplifier. And let's see how the amplifier helps. So what are the observations in this amplifier setup that you see here? What is one key critical thing that I have done in this amplifier? Can somebody tell me what is? So this is an amplifier. This is an ideal amplifier A, but I have connected it in a certain way. So what sort of a configuration is this? Anyone, guys? What sort of a configuration is this? Is it an open loop configuration, closed loop configuration? If it's
Sir, closed loop.
give me some response. Closed loop. And why is it a closed loop? Why do you call that closed loop, Ayush?
Sir, because the input and one of the output point are joined by feedback resistor and capacitive circuit.
Correct. Correct. So there is a feedback from the output to the input, right? Note one thing, this resistor we'll discuss about the resistor. This resistor is very interesting and why it is there and what kind of problem again the resistor creates. We'll discuss that. But I've kind of blurred the resistor, right? But what Ayush is saying, which is of course correct, we can see that there is a feedback. And why there is a feedback? Because the output, whatever output voltage we get here, some portion of that. So if, for example, if the output node is going high, we give that information to the input also. So if this node goes high, because of the capacitive coupling from the output to the input, this node will also tend to go high, right? Because it's a capacitor. The job of the capacitor is not to let the voltage across the terminals change, right? So if you are pulling one terminal up, the other terminal of the capacitor will try to follow, right? As long as if it's a hard connection, then it can't follow. If it's a ground connection, then it can't follow, right? But here in this case, it is not a hard connection. So it's a feedback. But what kind of feedback? Ayush, any comment? What kind of feedback? Ayush, Nayan, Shubham, anyone?
Negative.
The negative feedback.
Okay, so why is it a negative feedback, or how am I identifying it? Is it just because of the polarity that it's negative we are identifying? In this case, yes, you can simply say that, this is a negative feedback, right? Because it is connected to, the negative terminal. But how else do you think we can say that if it's a negative feedback or not? For example, if the same amplifier, come again, please, Shubham.
So by looking at loop gain, if it is negative, then it will be negative feedback.
Loop gain is one thing. Okay, I'll take that. But let me give you a twist to this. So let's say I have an NMOS. So I have another amplifier. And let's say this is my RL load. So this is also VCC or whatever you guys call it. You guys call it VCC. In industry, we call it VDD or whatever. So, and here, the same setup, I'm just drawing only this portion of the amplifier, okay? So this is negative, this is positive. Again, this is grounded. This is grounded because this is what I have done here, right? So what sort of a feedback is this? This is an NMOS. Why this is positive, and how can you say it so quickly, Ayush? Meaning, I'm glad that you're saying it very quickly, but I would like to understand your thought process, how you can quickly identify it's a positive feedback. Go ahead, Ayush.
For only that op-amp, if it were connected to the output, then it will be negative, and that amplifier has a negative gain, so that effective negative, it will have a positive feedback.
Right. So good. So basically, it's the other way to look at it. So there can be much more complex circuits, and the way I typically quickly to understand, and this is again a very simple circuit that I give. But to quickly understand whether it's a positive or a negative feedback, what I typically end up doing is, so this is my output, right? So this is my output. So typically what I do is I will say, okay, let me assume the output is going up, and I will try to see because of the amplifier what the amplifier is trying to do. So this is my first assumption is, let's say the output is going up, meaning it is going up. I mean, I'm increasing the output. So because the output is going up, what will happen? I have a capacitive coupling here, right? So the bottom plate of the capacitor will also tend to go up. So this is trying to go up. We have an amplifier here. This is the negative terminal. So if the negative terminal voltage is increasing, what is going to happen to the positive? I mean, what is going to happen to the output? It's going to reduce, right? Now, if this guy is going to reduce, this is what, this configuration of the circuit is what? This is nothing but a, what configuration is this, guys? This is my input. Yeah, don't use common emitter, Ayush, and that is where we get a bad name as faculty members, right, of IIT, that in IIT, whatever we are teaching you guys, it's not relevant to the industry. So this is actually a common source. Common emitter, I understand why you are calling it a common emitter. Yeah, I understand, Ayush, so no offense. So so this is, we talk of a common emitter if we are using a BJT, right? Because this is my base, collector, and emitter. But here we do not call it, we are talking of an NMOS, so we call it as drain, source, and gate. And this device is essentially a 4-terminal device, which I've simplistically shown as 3-terminal. So it's a common source. And why do we call it common source?
Because like source is grounded and we are giving input at gate and receiving output at like
Yeah, so to that is true, but why do we call it common? What is there in common? I mean, what is the big deal about common? The word common. Common means something, right? Just because source is grounded, you are calling it common. Huh? I can say, no, it's a source ground configuration. What's the problem? Source ground configuration is fine, right? Any comments to that? Any one of you? Ayush, Shubham, Nayan? Shubham, go ahead.
So maybe sources, all voltages are measured with reference to the source, like VDS, VGS, and
Yes.
in fact
Yes.
that fourth
Yes,
terminal is also.
that is correct, Shumam. But one correction I would like to do on the softer side. As an engineer, it's okay to use maybe sometimes, but on fundamentals, when you are going out in the world, you will never use the word maybe. You are sure. You will say, because we are talking of fundamentals. We are not thinking about something here. I mean, in this class it is okay, but it's never, when you're going out and talking to people about fundamentals, there is no maybe. So the answer is, actually Shubham is correct. So the answer is, the reason why we call it common, because the input voltage, I have just written the input voltage as VIN, but essentially what have I done? VIN, I'm measuring it with respect to ground. What is the output voltage? The output voltage is measured again with respect to ground, right? So this is also ground. So between the input side and the output side, if I look at the transistor as a 4-terminal device, I have shown it as a 3-terminal, but what terminal is common? This source terminal is common, right? Because yeah, I can connect like this, right? The output and the input is essentially sharing a common terminal, which is the source. And that is the reason we call it common source. It's a little bit diverting from the actual topic of the discussion, but it's very important because I'm going to discuss extremely complicated instrumentation circuits going forward when we talk about ultrasound and all. And actually, this is my pet subject because this is what I've been doing for a living for the last 20 years, right? I mean, this is how I earn my money and my family ran on it. So Ayush, yeah, go ahead. You want to say something?
sir, but in that way the body is also grounded, so we can tell common body also.
Correct. So that's a very good observation. So why do we not call the body as a meaning? Why don't we bring the body in the picture? The reason is, one second. Let me erase this. So that's a very good observation. Anyone wants to answer? Sorry. Anyone wants to answer that? Why do we not call it common body? So his point is, Ayush, right? Who asked this question? Ayush, right?
Yes, sir.
Okay. So anyone wants to answer that? Maybe Shubham, do you want to answer that? You can have a go, no problem. So what happens, Ayush, is in many configurations, actually it is done, by the way. And I've worked in such designs where, I mean, of course, I've worked in many designs, but where the body, right? So it's a 4-terminal device, right? And it's an NMOS. So the body, if I'm representing the body like, having another terminal here, in many places you will see the body is not grounded. Even if the amplifier configuration is like this, right? The body is not grounded. It can be connected to some other voltage. It can be connected to some other voltage. And the reason why that is done is if you want to tweak the threshold voltage of this device. If you want to, say, threshold voltage of a device comes from the fabrication, I mean, let's say your friend Shubham works in the fab, he works in the factory and he manufactures the device. He controls the threshold voltage of the device by controlling the doping concentration, the gate oxide and all that, right? And let's say you are not working in the factory, you are working in a computer, you're trying to design circuit. You tell your friend Shubham, hey Shubham, can you reduce the threshold voltage? But Shubham doesn't like you and he says, no, I can't do anything for you. You do whatever you want. This is what I can do. So you need to have a control on the voltage. You need not always rely on the device guy, which in this case is Shubham, to be able to tweak the threshold voltage, right? So in many applications, you will see the body or the bulk. So there are many names for the body. We call it, sometimes we call it substrate, sometimes we call it backgate, sometimes we call it, bulk or body or whatever. But substrate is actually misleading. So we'll talk about this. It's already 8:57, but can we pick it up from here in the next class? And this will be an interesting discussion, and we can talk about a little bit more on this. Right, guys?
Okay, sir.
Okay, Ayush, so hold on to your question. I'm sorry. So basically, a quick answer to you, Ayush, is in many applications you will see the body is not connected to ground all the time, and yet, but that doesn't mean that this is not a source. I mean, a common source configuration, right? So the body is kind of you can say a less talked about terminal used for used for some other reason, or it is not under your control all the time. And that also we'll discuss, that even if you want to connect the body to some other voltage, in many applications you will not be able to connect, and why that happens, that also we can discuss. But for today we can stop, and thank you guys for attending, and hopefully many of your other friends also start attending. The attendance of the class is reducing. Maybe I'm not able to make the course interesting enough, but we will see. I'm trying my best, right? So meet you guys next time. And actually we have a lab class today afternoon, so see you there, right? Okay. Bye.